Okay, I want to talk about in this one higher order linear differential equations. So we've talked about first order. Remember there we use the method of integrating factors. We talked about second order linear differential equations. And we talked about some of the ideas there, like the superposition principle and the existence and uniqueness of solutions to initial value problems there. I want to just sort of describe those details in the context of higher order different linear differential equations. And so that we can talk about them coherently if we need to in the future. Okay, but I will say that the overwhelming focus of this course is going to be on second order differential equations. And the reason for that is because of how applicable they are to the real world. Um, for whatever reason, and maybe this is some kind of deep principle that I can't fully describe to you now, but or I can't fully elucidate because I don't really understand it. But for whatever reason, the many phenomena in the universe are second order in nature. Just consider, for example, Newton's second law, which is this incredibly important unifying idea in classical mechanics. That's a second order differential equation. Okay, so let's take a look at higher order differential equations. Higher order linear. Linear is crucial here for as a simplifying, narrowing assumption. Higher order linear differential equations, and maybe I'll just abbreviate this HOLDE when I feel like it. Okay. So what are they? They are going to be things of the form y to the n. So this is the nth derivative. Remember, when you put the number in the parentheses, that means you're taking that many derivatives of the function. And then we're going to have a bunch of terms which look like a function, and I'll call these functions, I'm going to use subscripts to index them. And to indicate that it's a function of the independent variable, all right, p sub n minus 1 of x. And then times the n minus first derivative. So you can see that this index here is paired with the order of the derivative that we're taking of y. Okay, and we keep going like this. I guess the next term would be p sub n minus 2 of x, y, the n minus second derivative of y, and we keep going like this all the way down to p sub 2 of x times the second derivative, which I might write as y double prime, plus p sub 1 of x times y prime, plus p sub 0 of x times the 0th derivative of y, which is a weird thing to say out loud, but all that is y. Okay, and this whole thing here is equal to f of x. Okay. Cool. Now, one perspective, I guess, that I can offer about this crazy thing here is sometimes it's convenient to think of all of this over here on the right, no, left, I mean, as an expression L of y. And I don't want to go into too much detail about this. L is what's called a linear operator. Okay, it's an operator because it's kind of like a function that eats functions. Okay, in this case, L eats y, and what it spits out is another function. What function? If we feed it y, well, if we feed it y, it spits out this crazy function. And this crazy thing here is a function of x. I know it looks like there's y's and there's p's in there, but all of these things are themselves functions of x that we are amalgamating or combining using sums and multiplications and derivatives and things like that. It all ends up being a function of x. So this thing here, L of y, is a function of x, and what we are asserting with this equation is that L of y is equal to f of x. Now, I also used another word. I said that this operator is a linear operator. And what that means is that essentially it obeys the superposition principle. Okay, so I'm going to state the superposition principles for higher order linear ODEs using this notation. And you'll see what I hope you'll see what I'm trying to get at here. So what is the superposition principle? it says the following. If, um, well, let me say it like this. If L of, no. Sure. If L of y1 is equal to f1, sorry, I just wanted to think through what I was going to say. If L of y1 is equal to f1 and L of y2 is equal to f2. So don't be freaked out. All I'm doing is taking, when I write something like this, all I'm doing is taking y1 and shoving it into this crazy expression here for y. Okay? So if we have this, then under the situation where we're talking about an L like the one above, okay, it's very important that it be a linear differential operator. Then we have that L of C1y1 plus C2y2, which, recall, if you're a physicist gal or guy, then we could refer to C1y1 plus C2y2 as a superposition of y1 and y2. And if you're a more mathematically oriented guy or gal, then we refer to C1y1 as plus C2y2 as a linear combination. Just two different phrases for the same idea. Okay? Then L of C1y1 plus C2y2 is equal to C1Ly1. Actually, you know what? We got to give this pride of place here. So let me move this over to here. This is equal to C1L. Oh, no, I can do better because I know what L of y1 is. It's f1 plus C2 f2. Sorry, I should have put a 2 there. Okay? So this is really useful to know because if you plug stuff into L, okay, it's like you're collecting data that you can then combine together through superpositions and learn new facts and generate new data. Okay. And in particular, if L of y1 is equal to 0, meaning that y1 is a solution to the homogeneous higher order linear differential equation. Remember, a linear equation is homogeneous if this f of x over here is 0. So what I'm saying is y1 is a thing which, when we plug it into the left-hand side of this equation, we get 0. So it's a solution to the homogeneous linear differential equation. So if we have this and we have L of y2 equaling 0, then L of any superposition of C1 and y1, of y1 and y2 rather, is also 0. And this really just follows from the above line, right? Because in this case, what's playing the role of f1 is 0, and what's playing the role of f2 is 0. So L of C1y1 plus C2y2, which is this, is C1 times 0 plus C2 times 0. But 0 times 0, C1 times 0 is 0, C2 times 0 is 0, and 0 plus 0 is 0. Okay, so we get 0. Hopefully that made sense. But that's the superposition principle. And I want both of these versions for later in life. Okay. Then there's the existence and uniqueness theorems. And I'm going to state it. But the main takeaway from the existence and uniqueness theorem is that you can think of the set of solutions to a higher order linear differential equation. So now recall, back in first order land, when we were doing first order linear differential equations and solving those using integrating factors, remember that we got usually a one parameter family of solutions, right? There was usually one constant, a C, or C, maybe we call this C1, I don't remember, but C, in the general solution. In the case of two-dimensional, in the case of second order linear differential equations, we found that the solution space was two-dimensional. There were typically two knobs, C1 and C2, that we were able to adjust. Okay, the upshot of the main point of the existence uniqueness theorem for higher order linear differential equations is going to be that for a degree n linear differential equation, the solution space is n dimensional. Okay, but the way that I'm going to say this is not going to indicate that at first. Okay, so here's how I want to say it. If we have this kind of differential equation, and a degree n linear ODE with and I'll say the coefficients, which are the p's here, with coefficients which are continuous on some interval and we say x naught is some point inside of this interval. Okay, then the IVP, the initial value problem, given by the differential equation together with initial conditions, which will look like, and I'll list them. You might have something like y of x naught being equal to some number, which we'll call y naught. You might have y prime of x naught being equal to some other number, which I'll call y naught prime, because for lack of a better notation. I guess it's a little bit weird because it feels like you're taking the derivative of y naught, but that's not what I mean. Okay, maybe I don't know how to indicate that. I could do y sub 0, 1, but you know what? You're just going to have to deal with it. This is just some number, y naught prime, okay? Shoot, it is really confusing. Oh well, you're not babies. Y2, no. Y double prime of x naught equals y naught double prime. Okay, and then we're going to go all the way down to the nth. So the nth derivative of x naught is equal to y naught, and I'll write this notation like this. Okay, this is a set of n equations. Oh, I'm sorry. It's n minus 1. Sorry. I messed up. Let me fix myself. I messed up bad. It's the last initial condition should be the n minus first derivative. My bad. Yes. So we have n equations here. How do I know we have n of them here? Watch, count 1, 2, 3, n. Yeah. So we have n equations here. That's nice. And those n equations you can think of being as like n constraints on the general solution, right? And so, what is the sorry, I should say the punchline before I have this discussion. My brain is not all together here. Then there exists a unique solution. Oh, sorry, this is not English. Here, let me read. If we have, then the IVP given by the differential equation together with these initial conditions has a unique solution. This is English. Okay. There's only one solution. Okay. So the way that you should think about this is as a statement that the solution space to a degree n ODE, linear ODE, is n-dimensional. Meaning that there are n knobs that you can kind of turn with freedom on the to obtain solutions, to obtain new solutions. So this n is analogous to the two constants that you're often seeing in the context of second order differential equations, linear differential equations, and analogous to the one in the case of first order equation, the one constant that you're able to tweak and adjust values on. Okay, and indeed, the way that you should think of this is these n equations here. These n equations are like n constraints on your general solution. To satisfy any one of them, you need at least 1 degree of freedom. So to satisfy n of them, you need n degrees of freedom. Okay, that's the idea. Yeah, let me leave it there. It's important. Maybe I'll make this note. It's important that the initial conditions have this kind of structure here, where we're always looking at the value of a function y and its derivatives at a fixed point x naught, the same point x naught. Okay, but other than that, there's no constraint you see on these numbers. Why not? Why not prime? Why not? All of these numbers here can be whatever they want to be when they grow up, okay? But as long as you have that, you always get a unique solution. And again, that's the indication that what we're dealing with when we talk about the solution space to a degree n linear differential equation is n dimensional, okay? Okay, that's enough for now. And in the next one, we'll talk about how to actually solve these things through examples.